Hi everyone. In this video I'll be demonstrating how to perform a one-sample t-test using SPSS version 28. And before I get started, I do want to mention a couple of things. First off, underneath the video description you'll find a link to the SPSS data that I'm using in this demonstration, so you can download a copy of the data to follow along. And you'll also find a link to a PowerPoint that is going to contain some additional information that you might find useful to supplement this presentation. Another thing to point out or to note are a couple of differences between SPSS version 28 and prior versions of SPSS. So one of the differences that I've observed between SPSS version 28 and 27 and before is the inclusion of both one and two-sided p-values. So whereas in version 27 and prior versions, the p-values that are given are only for a two-tailed test, as of SPSS version 28, now you have a p-value that's given for both a one-sided and a two-sided test. So if you're working with a previous version of SPSS and you were testing a directional hypothesis and you're only given the two-sided test, then you would need to divide that p-value in half to compare it against your alpha level. And that's not going to be the case in this version 28, because you'll have the p-value that's already printed out. It's not that complicated to work from the two-sided p-value to obtain the one-sided p-value, but they're giving it nonetheless in SPSS version 28. Another thing to point out is that as of SPSS version 27 and now 28, you are also able to obtain effect size measures in your output. So those effect size measures come in the form of Cohen's d and Hedges g, and also you can obtain, or the output will contain confidence intervals for those effect size measures. So this is really nice, because in prior versions of SPSS you wouldn't obtain those or be able to obtain those effect size measures, and so you would have to compute those manually. So let's go ahead and get started. Briefly, let's take a look at our data. We have fictional data from 20 students. Basically, we have reading scores, math scores, and social studies scores. And what we're going to be doing is comparing the mean reading, math, and social studies scores in separate analyses against a hypothetical population mean. And the basic idea behind this analysis is that we are interested in comparing the mean of the population from which our sample is drawn against the mean of a hypothetical population. So we only have data from one sample, hence the name one sample t-test, and again we're comparing our sample mean against this hypothetical population mean from whatever analysis that we're doing. So at any rate, let's go ahead and start off. We're going to begin by testing whether the mean on reading scores is significantly different from the mean of a hypothetical population where that mean is 45. So to carry out our analysis, we'll go to Analyze, Compare Means, and then go down to One Sample t-test. So I'm going to move the read variable over to this test variables box, and where it says test value, I'm going to type in 45. And so when I press OK, I get my output. And by the way, this is the first analysis that's reviewed in that PowerPoint. So if you want to open that PowerPoint up and for some additional details, you're more than welcome to do so. So in terms of our output, you'll see that we have some descriptive statistics that are given in this box up here. We have our sample size of 20. The mean from our sample on reading scores is 54.85. We have our standard deviation that's given here. The standard error of the mean is simply computed as a ratio of the standard deviation to the square root of our sample size right here of 20. In the next box we have our test results. So you'll notice first off we have this test value right here, which is 45, And the mean difference that's given is just computed by taking our sample mean and subtracting this null value, if you will, of 45. So that's why we end up with 9.85. And because this value is positive, that is indicating that our sample mean is greater than this hypothetical population mean of 45. So as we're looking at our output, you'll notice too that we have a t-value that's given right here, and this t-value is computed from our data. And the reason why this is important is that our test is relying on a sampling distribution of t. It's a theoretical distribution where it's basically a family of distributions that vary according to the degrees of freedom for your analysis, and the degrees of freedom is computed as the sample size minus 1. So you'll notice right here, with our degrees of freedom being 20 minus 1 or 19, we're using that particular distribution to test our data against our hypothetical population mean value. So the t-value that's given right here is formed as a ratio of the mean difference to the standard error of the mean right here. So that's how this is computed. And you'll notice that we have p-values. It says one-sided p and two-sided p. So because we are just simply testing whether our sample mean is significantly different from 45, we're not making a statement about whether that mean is higher or lower than that value of 45, only that there's a difference. And so when we specify our hypothesis in that way, what we're specifying is a non-directional hypothesis. Now we're pitting that non-directional hypothesis against a null hypothesis, where the null hypothesis is that there's no difference between the population from which our sample is drawn in terms of the mean of that population and a hypothetical population where the mean is 45. So we're always starting off from the null hypothesis, and ultimately we're trying to test whether our data departs far enough from the null for us to reject the idea that the null is in fact true and essentially adopt the alternative hypothesis. Keeping in mind, though, that the alternative hypothesis, if we do adopt it, is provisional, because it's always possible that if we reject the null hypothesis using our sample data, that rejection was a function of sampling error. And so it may be that the true state of affairs is that there's no difference between the populations. So as we're looking at this, we're going to be relying on the two-sided p-value right here. And what we do is we compare this p-value against an alpha level. So alpha is essentially our threshold, our tolerance for committing a type 1 error, where a type 1 error is basically just incorrect rejection of a null hypothesis. In other words, in this context, it would mean that we would be inferring that there's a difference in the means when in fact there's no difference. So typically we set alpha at a low level. The conventional level that's generally adopted is an alpha level at 0.05. And so we compare the p-value that's given in our output against this alpha level, and so if that p-value is less than or equal to alpha, then we would reject the null hypothesis and infer that there's a difference in those means. And so as you can see right here, the p-value is less than the alpha level, and so that would be consistent with a decision to reject the null hypothesis. So we are going to infer that there is a difference in means between the population from which our sample is drawn and a hypothetical population that has a mean of 45. Now other portions of the output, you'll notice that we have a 95% confidence interval that's given. This is a confidence interval of the difference in means. So if you recall, if we take our sample mean, subtract the 45, we get this mean difference right here. And so the confidence interval is an interval estimate that's formed around that difference in means that we have of 9.85. And so it's also possible to test our hypothesis that there's a difference in means using the confidence interval that's printed out right here. So keep in mind that the null hypothesis is that there's no difference between our means. So in other words, we would expect that there's no difference between 54.85 and 9.85. So that no difference hypothesis is if I take the mean from which our sample was drawn and that mean of that hypothetical population, if there's no difference, then that difference would have to be 0. So what we can do is say if 0, which is no difference, falls between the lower and the upper bound of this confidence interval, then that would lead us to maintain the null hypothesis and infer that there's no difference in population means. If 0 falls outside of the lower and the upper bound, then that would lead us to reject the null hypothesis and infer that there's a difference in means. And so because the 0 that we have right here falls outside of the lower and the upper bound, that's going to lead us to reject the null hypothesis. Now, we can also then go down to our output with effect sizes. So the point estimates that are given right here, this is for Cohen's d, and then we also have Hedges g, the point estimate for that. So conventionally, at least within the social and behavioral sciences, Cohen suggested the following values for making a judgment concerning the magnitude of the effect that we're looking at. And just keep in mind there are different types of effect size measures that are covered in his extensive book on power analysis. So Cohen's d and also by extension Hedges g, these are associated or used to talk about effect size in terms of mean difference. So the conventions that are used for these indices right here are not going to be the same as if you were using, say, Pearson's R or something like that. So just keep that in mind. So I'm going to be referring to Cohen's conventions with respect to Cohen's d. So he suggested that basically a Cohen's d value, an absolute value, that is roughly around 0.20, that would signify that you have a small effect that's being observed, basically a small difference in means. A value around 0.50 would suggest a medium effect, and then a value around 0.80 or larger would suggest a large effect. So with those in mind, if I look at the point estimates that are given right here, you can see that we have 0.952 for Cohen's d. That would suggest a large effect that we are observing in our data. And by extension, if we use that same set of conventions for Hedges, you can see that that would also suggest a large effect. You can also see that we have a confidence interval that's given right here, which is formed around that estimate. And so you can see that the lower bound for Cohen's d is 0.412. And so that would put us somewhere in the medium-ish range, I guess you could say, whereas the upper bound puts us in the large range with respect to the magnitude that we are observing. And we could draw a similar conclusion with respect to Hedges that's given right there. So at any rate, that is essentially our first demonstration of the one sample t-test. Now let's consider using our math scores variable. So for our second analysis, we're going to be testing whether the mean on math scores is greater than 42. So essentially our alternative or our research hypothesis is going to be that the mean on math scores is greater than 42, whereas the null hypothesis is going to be that the mean math score is equal to or less than 42. And because we're using the language of greater or less than in our hypotheses, that means that we're going to be working with, that means that our alternative hypothesis is essentially a directional hypothesis, and that's going to imply a one-tailed t-test. So to carry out our analysis using our math scores variable, we're going to go to Analyze. We'll go down to Compare Means and One Sample t-test. I'm going to reset this and move our math variable over to the test variables box, and where it says test value, I'm going to type 42. and we'll click on OK and look at our output. So now with our output, we can see that the mean on math scores is 52.45. There's our standard deviation of 7.21. Here's our sample size. When we look at our t-value that's given right here, you can see it's 6.478. Degrees of freedom is 19. And you'll also see right here we have our mean difference. And so that mean difference, again, is computed by taking our sample mean and subtracting this hypothetical value of 42. So you can see that our sample mean is greater than 42. So right off the bat, because this value is positive and it's consistent with our alternative or our research hypothesis, that's one bit of information that we're going to consult when it comes to determining whether or not we would reject or maintain the null hypothesis. But the other piece is to compare our p-value against our alpha level. So let's just say that we adopt an alpha level set at 0.05, and again, if our p-value is less than or equal to 0.05, then that would also be evidence that's consistent with rejection of the null. But keep in mind that because we are working with a directional hypothesis, which would imply a one-sided p-value or a one-tailed t-test, we're going to be using the one-sided p-value that's given right here, which is, it says p basically is less than 0.001. And so this value of 0.001 is certainly less than the alpha level that you see right here. So that's going to lead us to reject the null hypothesis. But just keep in mind, when it comes to interpreting your output, the p-value that's given in the output doesn't care about whether the mean difference is consistent with your directional hypothesis. So you'll need to consider both the p-value in reference to alpha and the direction of difference that's reflected in the mean difference when it comes to making a final decision as to whether or not you reject or maintain the null. So for instance, let's just say for argument's sake that our sample mean was less than 42. And let's say that our mean difference had a negative value right here. Well, our research hypothesis or our alternative hypothesis was greater than, but yet if we had a negative value that's reflected right there, even if the p-value would suggest that we reject the null, because the difference in means is in the opposite direction, that would actually lead us to maintain the null hypothesis. So just be careful not to just solely look at the p-value when it comes to making a decision about rejection of the null hypothesis, particularly in those cases where you're working with a directional hypothesis. All right, so now let's do one more example. So for our third example, we are going to compare the mean on social studies scores to a hypothetical value of 62. And our research or our alternative hypothesis is going to be that our mean is less than 62, and the null hypothesis is going to be that the mean is equal to or greater than 62. So to carry out our analysis, we'll go to Analyze and go down to Compare Means and One Sample T-Test. I'm going to click Reset here and move Social Studies over to the Test Variables box where it says Test Value. I'll type 62 and click on OK. And so just keep in mind that in this case we are testing whether our mean, our sample mean, is less than 62. So that less than terminology indicates that we are testing a directional hypothesis. So as we're looking, you can see we have a mean on social studies of 54.8, and if we subtract 62, you can see the mean difference is negative 7.2. And by extension then you'll see that we have a negative t-value that's given right here. So in terms of just the direction of the difference, we see that we are consistent with the directional hypothesis, but we also need to check out our p-value in reference to our alpha level. So again, if I adopt the standard or conventional alpha at 0.05, then in this particular case, you can see for the one-sided p-value, that p-value that's printed is certainly less than 0.05. So because that p-value is less than 0.05 and the difference in means is as hypothesized, that would lead us to reject the null hypothesis and infer that the population mean on social studies from the population that our sample was drawn is less than 62. And if we look at our effect size measures down here, you can see that our point estimate for Cohen's d, it says negative 0.773. And just keep in mind that that negative is reflecting the difference in means that we're observing in our data. But when it comes to interpreting the effect size, what we're focused in on is the magnitude of the difference, not the direction of the difference. So to interpret Cohen's d in this context, and also Hedges' g by extension, we're going to take the absolute value that's printed out to make that decision. So if we go back and we think about those conventions of 0.2, 0.5, 0.8 for small, medium, and large respectively, well, the absolute value of Cohen's d in our output would be 0.773, which is pretty consistent with a large effect. Also, if we look at the confidence interval that's given, you can see we have the negative values that are provided. If we take the absolute value of negative 0.264, obviously it's going to be 0.264, and so that's indicating right there that at that boundary, that's going to signify a small effect, whereas if we take the absolute value for the lower bound right here, then that's going to signal a large effect right there. So you can see that the effect size would range between a small and large effect. And basically a similar set of conclusions would be drawn if we just look at Hedges' g that's given next. Okay, so that pretty much wraps up this video presentation on the one sample t-test, and I appreciate you watching.